Section 2. Introducing containers. In the physical world, a container is a standardized unit of storage. Container sounds like a generic term, but its importance is more clear if you look at how containers changed the shipping industry. Before the introduction of the modern shipping container in 1956, transporting goods from one point to another was a challenge. Goods were shipped in sacks, crates, cartons, drums, casks, barrels, and boxes of various weights, shapes, and sizes. They often were loaded by hand into whatever vessel was carrying them. The vessel wouldn't know how much cargo it could take until all of the cargo was loaded. Transporting goods this way was slow, inefficient, and costly. Shipping containers revolutionized the shipping industry. Their uniform size made it much more efficient to load, unload, and stack them. Containers could also be easily moved between ships, trucks, and railroad cars. In this way, containers improved efficiency, increased productivity, and reduced costs. This is a great example of using abstraction to increase agility. Abstraction is a way of hiding the working details of a subsystem. It separates concerns to facilitate interoperability and platform independence. In the shipping example, abstraction means that the people involved in shipping are further removed from the details of the transaction. This abstraction applies to the people who send the contents and those who actually facilitate the shipping itself. They don't need to worry about whether items will fit in a given container or about the fit of the container onto various vessels. This concept can move from the physical world to the virtual world of computing platforms. Virtually, a container is a standardized unit of software designed to run quickly and reliably on any computing environment that runs the containerization platform. Containers provide operating system virtualization, or OS virtualization, so that you can run an application and its dependencies in resource-isolated processes. A container is a lightweight, standalone software package that contains everything a software application needs to run. For example, it can contain the application code, runtime engine, system tools, system libraries, and settings. Containers can help ensure applications deploy quickly, reliably, and consistently, regardless of the deployment environment. A single server can host several containers that all share the underlying host system's operating system kernel. These containers might be services that are part of a larger enterprise application, or they might be separate applications that run in their isolated environment. Increasing levels of abstraction are often associated with technical maturity. The move toward containers is part of the evolution of deployment models. In earlier phases, you had bare metal servers. You had to build the architectural layers, such as the infrastructure and application software layers. For example, you would install an OS on top of your server hardware. Then, you would install any shared libraries on the OS and then install the applications that use those libraries. This architecture was inefficient. In this model, your hardware costs are the same, whether you are running at 0% utilization or 100% utilization. All of your applications must compete for the same resources, and you must keep library versions in sync with all your applications. If one application requires an updated library version that's incompatible with other applications running on that host, then you run into problems. These shortcomings led to the use of a virtualization platform over the host OS. Now you have isolated applications and their libraries which have their own full OS inside a VM. This arrangement improves utilization because you can add more VMs to run on top of the existing hardware, which greatly reduces your physical footprint. The downside to VMs is that the virtualization layer is heavy. In this example, you now have 3 operating systems on the physical host server instead of 1. That means more patching, more updates, and significantly more space taken up on the physical host. It can also cause significant redundancy. You've installed potentially the same OS 3 times and potentially the same library 3 times. Containers improved upon the idea of virtualization. The container runtime shares the host operating system's kernel. You can use this arrangement to your advantage to create container images by using file system layers. Containers are lightweight, efficient, and fast. They can be started up and shut down faster than VMs, which means better utilization of the underlying hardware. You can share libraries when needed, but you can also have library isolation for your applications. Containers are also highly portable. Because containers isolate software from other layers, their code runs identically across different environments, from developing and staging all the way to production. Here are the key takeaways for this section of the module. A container is a standardized unit of software that contains everything that an application needs to run. And containers help to ensure that applications deploy quickly, reliably, and consistently, regardless of the deployment environment. Thanks for watching, and see you in the next video.